Very good morning, one and all. My name is Sri Rajita, lecturer in ACE, Government Polytechnic, Mamna. I am dealing third semester network analysis. Now, I am going to explain about Thevinins theorem. So, upon the completion of this period, we are able to know various networks theorems about Thevinins theorem and how to find Thevinins equivalent for a given network. So various networks theorems are Thevinins theorem, Norton's theorem, superposition theorem, maximum power transfer theorem. So all these theorems, why we are using all these theorems? Because for analyzing a circuit network, we have to find out the currents and voltages, power in each element. Second, we can analyze the circuit with the help of mesh equations, mesh current equations, or nodal voltage equations. We can analyze the circuit. So in some applications, for simplifying procedures, we can use other theorems. So the Thevinins and Norton's superposition theorem, maximum power transfer theorems. So wherever it is applicable easily, then we can use that theorem and that analysis for analyzing the circuit. So for that, some of the scientists proposed the theorems is Thevinins theorem, Norton's theorem, superposition theorem, maximum power transfer theorem, and reciprocity theorem. Now I am going to explain Thevinins theorem. What is Thevinins theorem? Thevinins theorem states that any two-terminal linear network having a number of energy sources, that is voltage or current or both, and resistances or impedances, can be replaced by equivalent voltage source in series with resistance or impedance. When the impedance is coming into the picture, in the circuit there is a capacitors or inductors are there, we are considering the impedance. If only resistance is there, there is no topic about impedance. So again repeating the statement now. Any two-terminal linear network having a number of energy sources and resistances or impedances can be replaced by an equivalent voltage source in series with resistance or impedance. This is the network. This is the theorem. So the equivalent voltage being equal to the open circuit voltage at the terminals. So the network is replaced by equivalent voltage source. How this equivalent voltage is coming? The equivalent voltage is being equal to the open circuit voltage at the terminals. And the resistance in series with some resistance. The circuit is replaced with some voltage source in series with the resistance. How the resistance is coming? The resistance is being equal to the resistance of the network between the terminals with all voltage and current sources replaced by their internal impedances. What is the internal impedance for voltage source for ideal case? It is 0. For current source, the internal impedance is, for ideal case, is infinite. So the resistance being equal to the resistance of network between the terminals with all voltage and current sources replaced by their internal impedances. Ideally, all voltages are short circuited and all current sources are open circuited. So by doing this, by calculating the resistance, equivalent resistance across the terminals is the resistance, and equivalent voltage across the open circuit terminals is the voltage source. See here a picture, a linear network containing some sources, resistances, impedances, or anything, whatever the circuit is, it is there. That network is connected with some load at terminals AB. A load is connected to the network at terminals AB. And this network can be replaced by a single voltage source in series with resistance. Whatever the resistances or impedances within the circuit elements anymore, but that must be replaced by a single voltage source in series with resistance is called Thevinins theorem. And this voltage of the voltage source is equivalent to the open circuited voltage across the terminal. Means the ZL is, the load is open and the voltage measured across the terminals AB. That is VTH. What is RTH? RTH is by short circuiting all voltage sources, by open circuit all current sources, and the impedance across the terminals AB is the RTH. So this is about the theorem. So where VTH is open circuit Thevenin's voltage across B and RTH is Thevenin's resistance measured across AB, and keep voltage source short circuit and current sources open circuit. RL is the load resistance. This is the statement of the Thevenin's theorem. It is very, very important to solve the problems. So the steps to find Thevenin's equivalent. First, to open circuit the terminals at which Thevenin's equivalent is desired. Calculated VTH across open circuit terminals by using KVL or mesh analysis. If simple circuit we can easily find out, but a complex circuit is there, we have to use the mesh analysis or a Kirchhoff voltage law. A simple means we can simply apply Kirchhoff voltage law and we can find out that. But if a circuit is very, very complex, then we have to go for mesh analysis and find out the open circuited voltage. And find RTH by removing RL by replacing all voltage source with SC and all current sources with open circuit. Replace the original circuit by Thevenin's equivalent circuit. Find the current through RL. IL is equal to VTH by RTH plus RL. Then find the voltage across the load. VL is equal to IL into RL. These are the steps for using Thevenin's theorem. Now I am going to explain this Thevenin's theorem with the help of one example. Find the current through 5 ohm resistor using Thevenin's theorem. So it's a simple circuit in this. Here two voltage sources are there. E1 is equal to 8 volts. E2 is equal to 3 volts. And the first voltage source 8 volts is in series with 1 ohm resistor. And second voltage source E2 is equal to 3 volts is in series with 2 ohms resistor. And these two voltage sources are connected in parallel and load is connected across these sources. That is 5 ohm resistor. Here the problem is find the current through 5 ohm resistor using Thevenin's theorem. We can easily find out by any other type, but by using Thevenin's theorem, the solution is find out the current by using Thevenin's theorem. So first I remove the impedance ZL from the branch. So then what will happen? Then the two voltage sources in series with some resistances are become parallel. Determine the open circuit voltage E across the break and remove each source of EMF and replace by its internal impedance, that is zero internal impedance is replaced by voltage source, means short circuited, and then determine the internal impedance Z looking in at the break. Determine the current from Thevenin's equivalent circuit. The 5 ohm resistor is removed as shown in figure. The open circuit voltage E across the break is now required. A network of figure A is redrawn from convenience figure B. I1 is equal to E1 minus E2 by R1 plus R2. That equal to 8 minus 3 by 1 plus 2. So that equal to 5 by 3. Current is 2 by 3 amperes. That is 5 by 3 amperes. See here, by removing the AB, the 5 ohms across the AB, the circuit becomes the two are connected in series. Now, the current flowing through this is 5 by 3 amperes. This both are opposite in direction, and 8 minus 3 by 2 plus 1, that is 5 by 3. And we are replacing with the circuit by a single impedance. So these two voltage sources are short circuited and 1 ohm and 2 ohms are connected in parallel, and that is 2 by 3, and the voltage source is 6 1 by 3. That means 5 by 3 into 2 ohms, that is 10 by 3. And ZL is across that. So this can be, current is 1.1177. Hence the open circuit voltage E is given by E is equal to E1 minus I1 R1, that is E is equal to 8 minus 1 2 by 3 into 1. So that is 6 1 by 3. So alternatively E is equal to E2 minus I1 into R2, that is 3 plus 1 2 by 3 into 2, that is 6 1 by 3. So the total voltage source is 19 by 3 volts and the resistance is 2 by 3 ohms. So that then Thevenin's, the removing each source EMFs a figure, the impedance Z looking in at break AB is Z is equal to 1 into 2 by 1 plus 2 is equal to 2 by 3. The Thevenin's equivalent circuit is shown in figure where current IL is equal to E by ZL plus Z, that is 6 1 by 3 by 5 plus 2 by 3, that is 1.1177, that is approximately 1 point. So in this way we are calculating a circuit by Thevenin's equivalent circuit. So now I am going to explain another problem. So find the Thevenin's equivalence at terminals AB for below figure. Find IL and VL. So here the load resistance is 3.6 ohms and 10 ohms DC source is applied to the circuit and 4 ohms, 6 ohms are connected in series. And at the terminals, that is across AB, we are going to connect a load resistance. So first of all, we have to find out the open circuited voltage, that is RTH, Thevenin's voltage. So for that, voltage source is short circuited and load is open circuited. So the circuit becomes, there is a 4 ohms and 6 ohms are become a parallel circuit. So then RTH is equal to 4 and is in parallel with 6 ohms. So here see, replace the 10 volt source with short circuit and apply open circuit at terminals AB, and 4 ohms and 6 ohm resistors are in parallel, and RTH is equal to 4 into 6 divided by 4 plus 6, that is 2.4 ohms. Now for finding VTH, that is Thevenin's voltage. So here it is, by open circuit, that A load resistance and the 10 volts is applied across 4 plus 6, that is 2 resistors are becoming in series. And the current is 10 volts by 10 ohms, that is 1 amp. And now that 1 amp current is flowing through 6 ohms, the voltage across the 6 ohms is 6 into 1 amp, 6 volts. See here, the open circuit, the terminals AB. Next, find VTH across AB. So I is equal to 10 divided by 6 plus 4. I equal to 1 amp. So VTH is equal to I into 6 ohms, that is 1 into 6, that is 6 amps, 6 volts. So VTH is 6 volts and the Thevenin's equivalent circuit is 6 volts is in series with 2.4 volts. And now the 3.6 ohms is connected across the Thevenin's equivalent circuit, and the current flowing through the load resistor is IL is equal to VTH by RTH plus RL. So RTH is 2.54 ohms and RL is 3.6 ohms. Then the IL is equal to 6 by 2.4 plus 3.6 is again 6, and IL is equal to 1 amp. And the voltage across the load resistor is IL into RL, that is 1 into 3.6, that is 3.6 volts. So in this way, like that, we are solving the problems of the Thevenin's theorem. So in this period, we have discussed about the various network theorems. They are not at all discussed, but just named the theorems, and we discussed only the Thevenin's theorem. So how to find the Thevenin's equivalent voltage and resistance, and drawings of Thevenin's equivalent circuit usage. So now I am going to ask some questions. Please answer the questions. So the Thevenin's theorem cannot be applied for linear networks, dissipative networks, passive networks, non-linear networks given network. See, I am repeating again. So Thevenin's theorem cannot be applied for linear networks, dissipative networks, passive networks, non-linear networks given network. So choose the correct answer. See, that cannot be applied for a passive networks because we have to replace the circuit with a single voltage source in series with the resistance. If a voltage source is not there in a circuit, then we cannot apply the Thevenin's theorem. So it cannot be applied for passive networks. The second question. Thevenin resistance RTH is formed by removing voltage sources along with their internal resistances and by short circuiting the given two terminals and between any two terminals. So check that and give the answer. That is the answer. So now the third question. The Thevenin's equivalent circuit consists of voltage source across branch impedance in series with Thevenin's resistance and parallel with Thevenin resistance. None of the above. See, already we discussed, and in Thevenin's equivalent circuit, Thevenin's voltage source is in series with Thevenin resistance. Some of the questions that is asked in final question paper is state Thevenin's theorem. Explain Thevenin's theorem. So what is Thevenin's theorem? Again I am repeating that. Thevenin's theorem is the theorem in any linear or bilateral network which is consisting of voltage sources and impedances or resistances that can be replaced by a single voltage source in series with some resistance or impedance, and it cannot be applied for a passive networks. And this theorem is very useful in most of us simplifying the circuits. Thank you.